What is Bradford assay? The Bradford assay is an experimental procedure developed by American biochemist Marion M. Bradford to determine the concentration of unknown protein in a solution. It incorporates the absorbance shift of the dye used in the assay, which is Kumasi Brilliant Blue. The principle behind the Bradford assay utilizes non-covalent interactions between the dye and the unknown protein in solution. Under acidic conditions, the initial red form of the dye is transformed into its bluer form by binding with the unknown protein being assayed. The binding is possible due to the van der Waals forces and ionic interactions that take place in the reaction. The unbound red form of the dye first donates its free electron to the ionizable groups on the unknown protein. This causes a disturbance of the protein's natural state and exposes its hydrophobic pockets. These newly exposed pockets in the protein's tertiary structure bind non-covalently to the nonpolar section of the dye by van der Waals forces. This, in turn, situates the positive amine groups in proximity with the negative charge of the dye. The bond between the dye and the protein is further stabilized by ionic interactions between them, strengthening the blue form of the dye. Therefore, the amount of protein dye complex present in the solution is the measure of protein concentration, which can now be estimated by utilizing its absorbance reading. The unbound form of the dye is red and has an absorbance spectrum maximum at 465 nanometers. The bounded form of the dye is blue and has an absorbance spectrum at 595 nanometers. The increase in absorbance from 465 nanometers to 595 nanometers is proportional to the amount of dye bounded to protein, which is therefore proportional to the concentration of protein present in the solution. Like most experimental procedures, the Bradford assay can be interfered by certain compounds in the solution. This includes SDS, sodium dodecyl sulfate, which may be left over from protein lysis, since SDS is a detergent used to lyse cells by disrupting their membrane bilayer. Another form of Bradford assay interference is from the concentration of buffer used when preparing the protein samples to be run, such as elution buffer used in protein expression. A high buffer concentration can cause an overestimated protein concentration. This is caused by the depletion of free protons from the solution by the conjugate base form of the buffer. The buffer concentration is not a problem if a low concentration of protein is used in the overall procedure. The advantages of the Bradford assay are: it is very easy and simple to follow. It is done in one step, where the Bradford reagent is added to a test tube along with the protein sample. After mixing well in incubation, the mixture changes to a blue color, and the absorbance of the mixture can be determined at 595 nanometers. The Bradford assay is also one of the fastest assays performed on proteins. The total time it takes to prepare and run the assay can be under 30 minutes, depending on how long the mixture incubates before reading. The linear graph acquired from the assay can be easily manipulated to determine the concentration of protein by using the slope of the linear regression of the data. The assay is also roughly 10 times more sensitive than comparable assays used to determine protein concentration. Using the Bradford assay to determine unknown protein concentrations also has its disadvantages. Since the plot of the data is linear over a short range and is often making dilutions of samples before the analysis, the error in one dilution is carried over in further dilutions, which results in a linear relationship that may not always be accurate. In addition, the assay can be inhibited by the presence of detergents such as SDS. However, this problem can be lessened by the addition of cyclodextrins to the assay mixture. The necessary materials used to run a Bradford assay include the unknown protein to be assayed, the Kumasi Brilliant Blue dye, the specific buffer to be used in each sample, such as elution buffer or sodium chloride, and a spectrophotometer to measure the absorbance of each sample. The standard procedure of Bradford assay is as follows. Prepare a blank, the standard concentrations of protein, and sample dilutions of the unknown protein with buffer to be measured. The buffer used should be the same buffer each sample is prepared in. Then add about 100 microliters of each sample prepared in milliliters of dye to a separate test tube to be measured. Be sure to let each sample mixture to incubate at room temperature for about 10 to 30 minutes for the reaction to reach completion. Next, adjust the spectrophotometer to measure the absorbance at 595 nanometers and blank the program. Measure the absorbance of each prepared sample at 595 nanometers. Lastly, plot the absorbance of the standards versus their corresponding concentrations. Use a linear regression of the data to calculate the concentrations of the prepared samples of unknown protein. Some sample BSA concentrations to use depending on the apparent concentration of the protein are as follows. For protein concentrations from 200 to 1500 micrograms of protein per milliliter, suggested BSA standard solution concentrations are 250, 500, 750, and 1500 micrograms per milliliter. For protein concentrations from 1 to 10 micrograms of protein per milliliter, suggested BSA standard solution concentrations are 1, 5, 7.5, and 10 micrograms per milliliter. The next step in completing the Bradford assay to calculate the concentration of protein is to use the absorption and concentration data obtained from the spectrophotometer. First, to find a standard curve of the data, use the selected concentrations of the BSA solutions used in the assays. The data is to be plotted with concentration on the x-axis and absorbance on the y-axis. Based on this data, calculate the line of best fit of the data and display the equation. Then, rearrange the equation of the linear regression to solve for x, which is concentration. Using this manipulated equation, input the absorbance of the protein solutions measured to calculate their corresponding concentrations. Be sure to only compute the concentrations of the protein solutions whose absorbance falls within the linear regression of the standard data. However, the concentration you calculated using the equation is not completely accurate. In order to attain the normalized concentrations, the dilution factor must be used for the concentration to make sense with the initial data. And there we have the general gist of what the Bradford assay is, does, and the procedure. Thank you for watching, and I hope this video helped you out.